Okay. Good morning. Thanks for waiting, Andre. First, to warm you up a bit, does anyone remember this? Hands up. Okay, now, has anyone seen this? Okay. Does this remind you of anything? This is how we provision virtual networks in data centers. You call the networking guy, you politely ask him to provision a new VLAN, and the networking guy takes a patch cable and connects your server to the proper VLAN. Only the patch cables are virtual. Same concept. And what I'll talk about in the next 30 minutes or so is, do we really want to go from there and reinvent the phone exchanges, or is it smarter to just skip that step and go to Skype? And as Andre already introduced me, I'm Ivan, and I've been in this business since 1985, unfortunately. So I've seen every technology being reinvented like 3 times. And overlay virtual networking is no different. It's just old concepts reinvented with new names. What I'll talk about today is the features, not the futures. So I'll tell you what's operational today, what's shipping, and what people are actually using in large-scale data centers and cloud networks. I will not talk to you about the bright future that's out there, like 3 years out. So why are we discussing this? The only reason why you would want to consider something like overlay virtual networks is to build large, scalable, private or public cloud deployments. That's the only reason why you would want to sit in this presentation. Unfortunately, every one of us will have to start building them if you haven't started already. Because the old way of doing things just doesn't work anymore. All right, now let me try to move the mouse out. Okay. So why do we care about this stuff? Very simple. You know that once you start deploying applications that run on more than one single virtual machine, so once you start having applications that have multiple web servers and an app server and a database server and an authentication server and so on, you have to introduce the network services. So you need load balancers, you need firewalls in your application stack, you need layer 2 and layer 3 segments. So this is something like you would see in every single slightly larger application stack. You don't want me to show how the SAP architecture looks like. I couldn't decipher that. It's like a slide full of tiny little boxes all interconnected. And you have like 5 different zones, and every zone has like 3 different segments in there. So you don't want to see that. Now, when you move the applications into a cloud environment, ideally, you would support automatic multi-tenancy. So you would want to have the applications being totally independent, which is a mandatory requirement in public clouds, obviously. You don't want to have 2 customers sharing the same segment and sort of hijacking each other and breaking into the other infrastructure. So you want to keep the customers isolated. And even in private cloud, you really want to keep the applications isolated. That's one of the major mistakes we are doing these days. We are deploying, let's say, all the web servers in one single subnet, in one single security zone, and then we pretend that's secure. Now, let me tell you one thing. If I break into one of those web servers, I can probably hijack all the others and a few other things, particularly if you haven't disabled IPv6. In which case, I can start sending routing advertisements and hijacking the DNS server and a few other things. So it's really important that we have the same structure for every single application. And this is where things get complex. If you're an enterprise environment with like 10 VLANs, you can live with that. If you want to have like 100 applicames times 5 VLANs, it's already 500 VLANs. If you're a public cloud provider and you have thousands of customers, you're out of luck. And the traditional approach, I already mentioned it, are the VLANs. So yes, we have this thing that was invented 20 years ago to solve a totally different need, but let's reuse that because it's simple. And that's what the hypervisor vendors were doing for the last 10 years. They invested the minimum amount of effort they had to create a stupid, totally dumb layer 2 switch that was sitting in the hypervisor. And they got away with that because the networking industry was more than happy to support that stupidity to sell you more features. So we need something like layer 2 connectivity for 2 reasons between the virtual machines. The first reason is that we have to support the virtual machine mobility. So when I move the virtual machine from there to there, and the IP address cannot change, and I want to do this live, I really need layer 2 connectivity between the two. And the other one is floating IP addresses for things like load balancers. Unfortunately, because the TCP stack is broken and you really don't want me to go down that route, I have to tie my service to one IP address. And if that box breaks, I have to move that IP address to somewhere else. And to do that in real time, I usually need layer 2 between the 2 boxes, unfortunately. And, well, we already had layer 2 domains. They were called VLANs, and we use them. Everyone does. And everyone conveniently forgets that a layer 2 domain is a single failure domain. People sort of try to deny that, and I've seen a lot of customers who lost not 1 but 2 data centers due to a single forwarding loop. Because the consultants told them to implement long-distance layer 2 connectivity so they could move VMs from one data center to the other. Of course, they never used that feature, but they did lose 2 data centers. Great job. The other things we have to deal with is, like, we only have 4,000 VLANs, and with VLANs, we see all the MAC addresses in all the switches, usually, which sort of exhausts the forwarding tables on the switches, and then they go crazy and start flooding all the nasty stuff. And because the networking team and the server team couldn't possibly talk to each other, the networking team just gives up and gives the server people like 1,000 VLANs on every single server port, which sort of works okay, but it also turns the whole data center into a single failure domain. Another great job. And people who write RFCs and develop new technologies are more realistic than the marketing people who write the white papers. And so this is actually a quote from the Trill RFC, which is promoting bridging. And still, they were realistic, and they said, well, you know, in a single broadcast domain, you could have around 1,000 hosts. That makes sort of sense, sort of. Remember, this is not 1,000 servers, this is 1,000 VMs. So if you have 1,000 VMs in your data center, you should really skip the rest of this presentation. You have no problem. If you have more than 1,000 VMs, maybe you should continue listening. The networking industry obviously has a solution to every problem. Sometimes they even have solutions in search of problems, but that's a different story. So to solve this problem, well, don't worry, we'll implement VM-aware networking, and it's called VM Tracer if you're Arista, and it's called VMFax if you're Cisco, and it's called Junos Space Virtual Control if you're Juniper, and so on and so on and so on. Everyone has something. EVB if you're HP. And then, of course, there's spanning tree, and everyone loves to hate spanning tree, so we'll solve that, don't worry. We'll implement Trill and SPB and Fabric Path and VCS Fabric and all that stuff. And that will also give us layer 2 ECMP routing, so routing at layer 2, which is a great idea. I mean, it sounds like square circle, but okay, I'm fine with that. And then, of course, we still have 4,000 VLANs, so either we'll add another VLAN tag or we'll add another MAC layer header. So we'll do MAC in MAC or Q in Q or something. So yeah, we'll get you there, don't worry. The only problem is, after all this stuff, we still have a single failure domain. So you have to implement like 6 totally new technologies that some people will tell you are totally proven and safe, but you've never seen them before. And after doing all this, you still have a voice exchange. You still have something that has all the complexity in the core. And by the way, this is not how internet works. That's why internet scales and these things don't scale. Okay? And of course, you can solve every problem by throwing more complexity at it. And Randy Bush is famous for loving that approach. So there's this RFC published on April 1st saying, with enough thrust, pigs fly just fine. And Randy Bush had to add, but remember who is paying for the fuel. You are. With the increased capex and increased operational expenses because you have to support these complexities. So can we do something better? Can we move from the traditional voice exchanges, which were expensive as we know, to Skype? Can we move another application on top of IP? Can we move virtual networks on top of IP like we moved storage and voice and video and everything else on top of IP? Can we move the complexity from the core to the edges? Because if you do that, then all of a sudden, all you need in the core is IP. And that's why the networking companies don't love this, because then you can just buy simple switches. But remember, complexity at the edge and simple core, that's how internet works. And I think that we can all agree that internet scales. I mean, we are using it and it works. So why don't we do the same thing here? When people started preaching this stuff like 3 years ago, myself included, everyone told us, you're crazy. Who wants another tunneling approach? I mean, we all hate tunneling, right? Anyone had to implement GRE tunnels? Hands up. Only that many? No, I thought it would be like everyone. Yeah, we all hate tunnels. So when people started talking about overlay virtual networking, the immediate response was, we hate tunnels. Go away. Now, in 2 or 3 years, the situation has changed totally. These are shipping products from major companies. So everyone has a product in this space. Of course, some networking companies are hedging their bets. If this fails, we'll still sell switches. If this succeeds, we have, we are part of the game. But everyone has something shipping. And I'm not talking about announcements. I'm not talking about white papers. These are things that you can buy or download and use. So for me, the criteria is, can I download it and can I get access to the product documentation? If I can do those two things, then the thing is shipping. Otherwise, it's vaporware. So let's see how this works. And I'll start with a simple part with a data plane. Oh, I can't point to anything. Too bad. So on the left-hand side, you have the VM that wants to talk to the VM on the right-hand side. And the two VMs think they have an Ethernet cable between them. So the two VMs think they are connected to that thick Ethernet cable. Anyone remembers the thick Ethernet cable? Good. So the VMs think they have that. And so the VM would send an IP packet with a MAC header because it thinks it's working on an Ethernet. And as the packet goes down through the virtual switch, which emulates a dumb layer 2 switch, remember, it will hit the encapsulation module, and the encapsulation module will just add an envelope. In the VXLAN envelope, in this case, we would have the virtual network ID, which is like VLAN, but 24 bits. So it's a bit bigger address space. And then VXLAN would use UDP for a very simple reason. We can hash the inside packet and put it into the source port, so we get the entropy we need for load balancing in the network core. That's why VXLAN is slightly better than GRE, where you don't have the entropy label. And then the whole thing goes down the stack, hits the TCP stack, gets the outer IP header, and it's sent across to the other hypervisor. Now, I sort of hand-waved over a detail. I didn't tell you how I figured out what the destination IP address is, right? Now, a good magician wouldn't tell you that. But I'm honest, so we get to that part in a few slides. So eventually, the IP packet arrives to the other end. And now here in the middle, you could have any number of routers. This is IP. So you could get rid of large-scale VLANs in your data center. You could really start using layer 3 switching, also known as routing, within your data center. And as the thing goes up the stack, eventually it arrives to the target VM and is delivered to the target VM as an Ethernet packet. And I already mentioned 2 encapsulations. The third one from Nicira, that was bought by VMware, is STT. And 2 years ago, we had this huge discussion which one is better. And honestly, that discussion was interesting but totally stupid. Because all the encapsulations do the same thing. You have the outer IP, you have the inner payload, and you have something in the middle. And that something in the middle differs only in a few bits. And vendors have realized that that's a stupid discussion. So right now, for example, VMware's NSX supports all 3 encapsulations. Choose one. There are tiny technological differences. If anyone is interested, find me after the break and we'll discuss that. From the overall perspective, it doesn't matter which one you use. Do remember that none of them has any security. So it's like VLANs. If someone breaks into your data center core and connects to a core port, to a trunk port, he can inject traffic into any VLAN. The same thing here. If someone breaks into your IP core, he can start injecting traffic into any virtual segment. So your core must be absolutely secure. I hope it is, otherwise you have a different problem anyway. And what matters most, now we know that the encapsulations don't matter, so what does matter is the control plane. So how will one hypervisor figure out where the other virtual machines are? And how will that hypervisor figure out what destination IP address to use when it sends the IP packet? You know, it's like the thing when you do a Skype call. How do you figure out the IP address of the guy you want to talk with? That's what matters. Everything else is dirty details in the data plane. And the first implementation was surprisingly stupid. What Cisco did when they shipped VXLAN was they just reinvented Ethernet. They decided to have no control plane and rely on flooding to learn the MAC addresses of the other VMs. So it's exactly like Ethernet with flooding, only instead of broadcast in the transport network, we use multicast, which is slightly better than broadcast, but it requires you to implement multicast in your data center core. And if you don't already have multicast, and only some financial institutions have that for stock exchange feed distributions, then of course you aren't that happy about implementing multicast just to support this new thingy, right? How many of you had to implement multicast in your life, in real life networks? Amazingly high number. I've only seen it on the CCIE lab. So, VXLAN without a control plane relies on flooding and learning. And by the way, to be honest, since June, Cisco is shipping a unicast-only VXLAN with proper control plane. So how does that work? Imagine that the 2 VMs want to talk to each other. And the first thing you need to do in the IP world, you have to figure out who the other guy is. You send out an ARP request. So you send out an ARP request, which is a broadcast. And that broadcast is flooded by using multicast in the transport network. Of course, every hypervisor that has the virtual machines in that segment has to listen to those multicasts. So there are IGMP joins and so on going on in the background that I'm conveniently ignoring now. And so eventually that multicast arrives to the other end. As it goes up the stack, an important thing happens. The destination hypervisor remembers the source IP address and the source MAC address. So by receiving this flooded packet, the destination hypervisor has built the mapping between the source VM MAC address and the source hypervisor IP address. Just like regular Ethernet flooding. You use the flooded packets to build the topology. Same thing here. And then the ARP request is delivered to the VM, and when the VM sends a unicast reply, the right-hand hypervisor already knows how to get to the left-hand hypervisor, and when the ARP reply comes back, the left-hand hypervisor does the same dynamic MAC learning, and so now the two VMs can communicate. That doesn't scale. And we just moved the problem from the virtual networks to the physical network. So now every single vendor has already implemented some sort of control plane. And people are using either totally proprietary protocols like Cisco or now VMware with NSX for vSphere, or they are reusing stuff like MPLS VPN, like Juniper is doing with Contrail, or Alcatel-Lucent is doing with, what's that thing called, Nuage, I think. And the original Nicira's network virtualization platform was using OpenFlow, because the guys who did this stuff were heavy proponents of OpenFlow. And I think I was talking about OpenFlow like 2 years back at PLNOG, so you should know what that is. So what they have is they have an OpenFlow-based network, and they're adding additional components to implement NAT and layer 3 and firewalls and so on. Yet again, if you need to have more information, talk to me after the break. And now I did a webinar with VMware a week or so ago. So all this information will be published on the web, and you will be able to download it. It's like 3 hours worth of content describing how this thing works. So one slide in 3 hours. And just to let you know how this thing works in a bit more details. So let's say we have some tunnel between the two hosts with that VM. And by the way, when I use the word tunnel, don't be afraid. This is not something you have to configure. This is not something you have to manage. This is not even a Linux interface. It's just a logical construct like a TCP session. You don't manage individual TCP sessions on a web server, do you? Oh, hopefully not. So you don't manage these tunnels by yourself. They are just logical constructs, because OpenFlow is a protocol that was designed to work on switches. And switches have point-to-point links, right? So if you want to emulate point-to-point links, you need tunnels, right? Okay, so we have that tunnel there, and now the orchestrator like OpenStack, for example, has started a new VM. It placed the VM on the third host, and now we need to connect these 3 VMs. So what happens is when the orchestrator tells the network virtualization platform, which is now VMware NSX for multi-hypervisors, that there's a new VM, first we need the tunnels. So there are 2 daemons in that box, and one of them is using so-called OVS database protocol, OVS-DB, which is the configuration protocol, because the guys that invented OpenFlow forgot about configuration. We don't need that, do we? So we need that configuration protocol, and then the tunnels get established. So now we have the full mesh of tunnels, and now we can program the forwarding entries through OpenFlow. And these are the forwarding entries. As you see, very simple. If the MAC address equals MAC C, then go to that tunnel. If it equals MAC B, go to that tunnel, and so on. So very simple concepts that allow you to implement a totally static, deterministic network. So there is no learning and flooding here. Well, they do flooding, but they use a different mechanism for that. And because this whole thing is deterministic and proactive instead of reactive and responding to traffic flows, they can scale at the moment to 5,000 hypervisor hosts with a single controller cluster, which is sort of cool. Of course, by now you should be asking a different question. Okay, I love this, but it's tunnels, right? So how do I connect this thing to the outside world? That's where the problems start. So, of course, the existing hardware doesn't support these new encapsulation types. Because if you want to add a new header in front of a MAC packet, you need to support that in hardware. You really don't want to do that in software, as everyone who ever had to do software-based switching on a Catalyst 6500 knows. So we need to support this in hardware, and hardware support just isn't there. So the only two companies that have shipping hardware after promising it for 2 years, let's be honest, are Arista and F5. And everyone else is still promising. Yes, we are actively committed to this. Yes, sure. I collected a few quotes for your enjoyment. But by the way, don't be so focused on the hardware. Because what you really need to connect the virtual world to the physical world are usually things like load balancers and firewalls. There is some need for layer 2 gateways and layer 3 gateways in migration scenarios, but you really usually want to have a load balancer at the edge or a firewall at the edge. Now, if you open any firewall these days, what do you see inside? Intel chipset and Intel interface cards, and maybe a tiny little bit of ASIC. And the only thing that ASIC does is it distributes the packets to different CPU cores. So, what's the difference between a physical appliance and a virtual appliance? Well, the price. I did some calculation based on what I got from publicly available Palo Alto price list. And the physical hardware that supported 20 gig of throughput, or 10 gig, or whatever it was like 3 or 4 times more expensive than just buying the licenses from Palo Alto for the same stuff. And then I threw a huge HP server at the problem, you know, that thingy. And I still had like $30,000 left. So if I would use more reasonable servers, I would have maybe like $50,000 left at the end. Of course, you do end up with more boxes to manage. So you don't manage one physical firewall, you will have to manage 10 virtual firewalls. But do remember that managing 10,000 firewall rules on a single physical box is not fun anyway. So, focus on the VM-based appliances. Performance is reasonable. Feature set is reasonable. Sometimes you can get the same thing in physical or virtual format, particularly from vendors that are trying to get market share, like Palo Alto or A10. And you get flexibility, because you can deploy them as you need them. You don't have to buy this huge box because you don't know what you will need tomorrow. So how does this work? Well, the packet in the overlay world arrives to the appliance, and the appliance thinks it's connected to 2 physical networks. The appliance has Ethernet cards, and those Ethernet cards are connected to somewhere, and one Ethernet card could be connected to the virtual side, and one Ethernet card could be connected to the physical side. So as the packet goes from the VM down the stack toward the appliance, it eventually ends up at the appliance, firewall in my case. And the packet ends up as an IP packet, regular IP plus Ethernet packet at the appliance's inside NIC. And then the appliance does its stuff, whatever the stuff is. And maybe decides to send the packet out. And if the outside interface happens to be connected to a VLAN, then that packet will get a VLAN tag, and we're out in the physical world. Problem solved. And now let's put all this together. How would I deploy this? First of all, and I'll talk about this tomorrow, I think afternoon in one of the tracks I have a how to not build a cloud session. You don't deploy this on your existing infrastructure, hopefully. Sometimes you will have to, but if you have the option of starting from scratch, then you build a leaf and spine fabric so that all the endpoints have the same bandwidth between them, so you don't have any bottlenecks anywhere. And then you just connect servers to that leaf and spine fabric, and you dedicate some servers to host the virtual appliances. Now, some people are saying, well, why don't you just spread the virtual appliances all over this thing? And there are two reasons. The virtual appliances have a totally different workload requirement than the regular VMs. So they need little RAM and loads of I/O throughput. So mixing them with the regular VMs is not a good idea. Plus, you will always get complaints from your security people. How this is insecure. How could you be so crazy to even think about deploying firewall and a customer VM on the same box? You must be crazy. Now, if you move all the firewall VMs to one server, then you can easily ask the security guy, okay, now do explain to me, how is this different from a physical firewall? It's running the same software. Sorry. So do keep the appliances separate in a separate cluster. Okay. So I hope by now you know where you could use the overlay virtual networks and where they do and don't make sense. And I try to put things together in sort of a graph explaining how scalable individual solutions are. And the graph is not up to scale because I couldn't make VLANs small enough. So VLANs, obviously, try to get rid of them as soon as possible. VM-aware networking and EVB and stuff like that, yeah, that helps if you have to deal with VLANs, but try not to go there. So the first thing that makes sense from the scalability perspective is Cisco's VXLAN, also available now in vShield, well, vCNS with vSphere 5.1 from VMware. That thing has requires IP multicast, so you really want to move one step down to unicast VXLAN. The only problem of unicast VXLAN is that it's totally proprietary, either Cisco's implementation or VMware's implementation. So the moment you move down to unicast VXLAN, you're in a single vendor environment. Or if you want to move further down the scalability graph, VMware's NVP, or now NSX, has layer 2 and layer 3 segments with a proper control plane. And as I told you before, that scales to 5,000 hypervisors with a single controller cluster. With 20 to 100 VMs on a hypervisor, that should be good enough for most people, apart from Amazon and a few others. If that's not good enough, you can try one of the layer 3 only solutions, which is Juniper's Contrail or Microsoft's Hyper-V network virtualization. They are pure layer 3 solutions, so there's no flooding. And even VMware with NSX reduced flooding to the very minimum. They have local responses to ARPs, so ARPs are not flooded anymore. So all 3 solutions are almost floodless. So it's just the question of the quality of the software implementation, who scales better. And finally, where should you use this? Well, if you're building if you're building a public cloud and you're not considering this yet, then you're late. If you're building a private cloud, you should really focus on virtual appliances and overlay networks, because that will make your cloud flexible. Don't get tied into physical boxes. Now, if you're a more traditional shop, you're still doing server virtualization. overlay virtual networks are worth considering if you're willing to move to the virtual appliances. So personally, I wouldn't buy hardware load balancers today. I wouldn't. I would buy licenses. It doesn't make sense to buy hardware. x86 servers are cheaper. Okay? And I'm not saying that you should buy from vendor A or B or C. Almost all of them have their appliances in VM format. Once you get there, once you start using the virtual appliances, then you're ready for the next step, which is the overlay virtual networks. And once you get there, and you know, people are always worried like, okay, what will I do now that I don't have VLANs to provision? Well, be happy. You won't have VLANs to provision. You will actually do something with your life. So there is enough work in networking. VLANs aren't the only thing we are doing. So be happy when you get rid of them. And of course, if you have the traditional organization where the storage and the networking and the compute people don't talk to each other, then maybe it's time you change your job. And by the way, if you want to know more, I have a number of webinars on this topic, so go to my website, find them. And I would strongly recommend that you start reading these blogs if you don't read them already. So the PDF will be published, so you'll have the whole list there on the PLNOG website, so you can start following them. And if you have any questions afterwards, I'm always available on my email, or you can send me a tweet. And I try to respond to every single email. Sometimes I just get a burst, and then they sort of drop off the screen. So just resend, please. And if you have questions now, we have a question there. Yeah.
Jan George.
Good morning, Jan.
Good morning, Pippi. So, okay, you're talking about the IP transport here. So can you tell us how many of the shipping products can use IPv6 as a transport and multicast as a control plane?
You want the combination? None.
Okay. Okay. Skip the multicast.
Okay. One. Would you want to guess who it is?
Cisco.
Microsoft.
Oh, really?
Microsoft.
Oh dear. Really?
Hyper-V network virtualization supports IPv4 and IPv6 both on transport and on virtual networks. And they do layer 3 forwarding for IPv4 and IPv6 in the hypervisor.
Maybe I should start looking into Microsoft products.
Yeah, you should.
Okay,
Stop hating them.
Thank you.
Hi, Ivan, David Friedman here. I have a question. I think you may have been almost encouraging the construction of bridged layer 2 between data centers.
Oh no,
And that really worries me.
No, but by the way, sorry. Do not use this as layer 2 extension between data centers.
Thank you.
It does not work.
Thank you very much. Applause.
Thank you for pointing that out.
Ivan?
Yeah.
Question here, Piotr Jablonski speaking. How do you address in your solutions clusters which requires multicast? Because in IP solutions you need to send n times something or convert this cluster to unicast mode.
So if you're talking about Microsoft NLB, kill it with fire. Microsoft NLB shouldn't be used. People invented load balancers for a good reason. Now, if you want to have multicast in the virtual network for whatever reason, then all the layer 2 solutions implement flooding, and then you have to decide how much multicast are you going to see. So if you have an occasional multicast like the cluster heartbeat, then source-based replication is usually good enough. So you don't need multicast in the transport network. For those few heartbeat packets, you just send multiple copies of unicast to all members of that virtual segment. If you have heavy multicast, then obviously you have to start looking into optimizing that. And for that, you either use multicast in the transport network, and you can do that with VXLAN, both Cisco's and VMware implementation, as well as with Microsoft's Hyper-V network virtualization.
Because frankly speaking, when I am attending data center projects, everyone has a requirement, please, this network should be ready for the multicast. Even though there are not really content for it, they would like to be prepared. So multicast is a part of data center.
Well, it's part of RFP process. It's tick in the box. I know that. So yes, you can support it in almost every one of these solutions. Does it make sense is a different story.
Thank you.
I've got this very simple question about this ideology of tunnels. If I counted in my mind correctly, if your network grows, the number of tunnels grows as a square function. So,
yeah. Well, even worse if you have IP routing involved, but yes.
So how large can the network be working correctly, properly?
Well, first you have to remember that, thanks for the question, it's a really good one. You have to remember that these tunnels are not the traditional tunnels that we love to hate. These are not the GRE tunnels that you have to provision manually. Think of these tunnels as TCP sessions. The network core doesn't care about the number of TCP sessions transported over the network core. The network core cares only about the bandwidth consumed. Okay? So these tunnels, they leave no state in the physical hardware. It's just traffic going between IP addresses on the edges. So from the physical hardware standpoint and the state in the physical hardware, it's no different than having TCP or UDP traffic. Now on the hypervisor side, if you're using layer 2 domains, so layer 2 segments, then obviously the maximum number of tunnels, worst case, that you would have on a single hypervisor is the number of VMs, assuming each VM is a different segment, times the average segment size. So let's say we have 50 VMs on a hypervisor, and each VM is in a different segment of 50 VMs. Worst case, that would be 2,500 tunnels. And these are not even Linux interfaces in Nicira's case. In other implementations, these are not even, you can't even see these tunnels. These are just mappings in the MAC to IP mapping table. Yeah.
Sorry, I didn't say that my name is Tomasz Ligocki from Nazwa.pl.
Last one question.
Jan George. So, are we again at the socket that you love to hate?
Of course.